Welcome to the Deep Dive, the show where we distill complex research into, well, hopefully, crystal clear insights.
Hopefully.
Today we're diving into a paper that's genuinely causing quite a stir. It tackles a really fundamental problem in computer science, finding shortest paths in graphs.
Yeah, it's one of those ancient problems. And for decades, Dijkstra's algorithm, it was just the gold standard. Super efficient, mostly.
Mostly, yeah. But it always seemed to hit this wall, this thing people called the sorting barrier.
Exactly. Which kind of limited its speed, especially on sparse graphs, to OM plus n log n, m edges and vertices.
And the thinking was, well, if you need the shortest paths to all the places,
Right.
you sort of have to pay that sorting cost, right? So Dijkstra's looked optimal.
That was definitely the consensus. But this new paper, Breaking the Sorting Barrier for Directed Single-Source Shortest Paths, it just throws a wrench in that, for directed graphs anyway.
Oh, more than a wrench. I mean, they've properly shattered it. They're announcing a new deterministic algorithm, get this, OM log n time complexity.
Which is just wow.
Yeah.
It's a huge shift. It basically proves Dijkstra's isn't the final word if all you care about are the distances themselves, not the full sorted order of vertices.
Right. It decouples finding the distances from the sorting process itself.
And the way they did it is really neat. It's like a clever mashup combining the best bits of Dijkstra's with the Bellman forward algorithm.
Using techniques like recursive partitioning and something they call frontier reduction. Sounds technical, but we'll unpack it.
Yeah, we will.
So stick around if you're into AI, machine learning, network optimization, or frankly, if you just love seeing long-held assumptions get turned on their head. We're going to explore how they pulled this off. Okay, so we mentioned this barrier, this sort of speed limit. Let's step back a sec and really define the problem space. The single source shortest path problem, SSSP.
Right. Sounds fancy, but the core idea is simple. You've got a map, basically a graph. Pick one starting point, the source.
Like your home base.
Exactly. And you want to find the absolute shortest route from that home base to every other possible destination or vertex on the map. Assuming you can get there, of course.
And specifically for this paper, we're talking directed graphs, right?
Yeah.
Like one-way streets.
Yep, directed graphs. And the cost of traversing a street, the edge weight, is a real non-negative number. No negative costs allowed here.
Okay, no time travel allowed by going down a negative street.
Yeah, exactly.
Yeah.
And importantly, the algorithms here work in what's called a comparison addition model.
Meaning
The only things the algorithm can do with those edge weights are compare them, which one's bigger, and add them up. Each comparison, each addition takes 1 unit of time.
So no fancy math tricks based on how numbers are stored in the computer.
Precisely. It makes the result much more fundamental and widely applicable.
Yeah.
It's about the structure of the problem, not some loophole.
Gotcha. And this SSSP problem, it sounds fundamental, but maybe you could give us a feel for where it actually crops up beyond, mapping apps, especially for folks listening who are deep in AI or ML.
Oh, it's everywhere once you start looking.
Right.
Think about robotics. A robot figuring out the most efficient path across a factory floor. That's SSSP.
Okay.
Or in reinforcement learning, an agent navigating a huge state space to find the best sequence of actions.
Yeah.
Often involves shortest path ideas.
Right. Minimizing cost or maximizing reward.
Exactly. And for ML engineers, think about analyzing social networks, understanding influence spread, or even some graph neural network architectures rely on efficient path computations. It's a building block. Improve the block, and lots of things built on top get better.
That makes sense. So it really does ripple outwards. Now, Dijkstra's algorithm, it was the king for so long. Can you give us a quick refresher on how it actually works?
Sure. Dijkstra's is quite elegant. It works iteratively. It keeps track of vertices for which it's already found the definite shortest path.
The finalized set.
Right.
Okay.
And then it has a candidate set, usually managed with a priority queue, holding vertices it's reached but maybe hasn't found the absolute shortest path to yet. At each step, it pulls the vertex with the smallest tentative distance out of that priority queue. That distance is now declared final.
Because there's no way a path going through something further away could possibly loop back and make it shorter, given non-negative weights.
Exactly. Then it looks at all the outgoing edges from this newly finalized vertex. This is called relaxing the edges.
Relaxing. Sounds nice.
Yeah. It just means checking. If I go through this new vertex, can I reach its neighbors with a shorter total path than whatever path I knew about before?
Okay. So you might update the distances for its neighbors in the priority queue.
Precisely. And you keep doing this, pull the minimum, finalize, relax neighbors until the priority queue is empty. Or you found paths to all reachable vertices.
And with things like Fibonacci heaps, it gets down to that OM plus N log N time, which is pretty fast.
It is. But here's the crux. That act of repeatedly pulling the minimum element from the priority queue, that's inherently a sorting operation.
Right. It doesn't just find the distances, it finds them in increasing order from the source. It gives you that sorted list as a byproduct.
Exactly. And that byproduct seemed unavoidable. There was even recent theoretical work, like from Haupler and colleagues, suggesting that if you needed that specific sorted order, Dijkstra's was optimal.
Implying a lower bound, like N log N, similar to sorting N items?
Yeah, basically saying you can't really do better if that sorted order is required. It seemed like a fundamental truth, especially for deterministic algorithms on directed graphs.
So people had found ways around it for undirected graphs, maybe using randomization.
Right, there was work by Petty and Ramachandran and a randomized approach by Dewan et al. For undirected graphs. But the deterministic directed case, that barrier held firm.
Until now.
Until now. This paper comes along and bam, theorem 1.1, a deterministic algorithm, OM log on time, directed graphs, non-negative real weights.
Okay, let's talk about that exponent element. How much better is that really than log N?
It's significantly better, especially as n gets large. Think about it. Log n grows really slowly. Log squared of n would grow faster. But log to the power of 2/3, that grows even slower than log n itself.
Ah, okay, so the bigger the graph, the bigger the relative advantage gets.
Exactly. It's a genuine complexity improvement. And the really cool thing,
What's that?
it's not just the first time breaking the barrier for directed graphs deterministically.
Right.
It's actually the first deterministic algorithm to beat OM plus n log n, even for undirected graphs too.
Wow, okay. So it solves both problems in one go, essentially.
Yeah, it's kind of a 2-for-1 deal,
Yeah.
which is just remarkable in such a mature area.
And you mentioned it's not a completely new thing, but a mix of Dijkstra and Bellman-Ford.
Right. It takes the good parts of both. We talked about Dijkstra's bottleneck.
Mm-hmm.
The priority queue, the frontier of nodes it's managing, can get really big, like almost all the nodes in.
And constantly finding the minimum in a huge set is slow. That's the N log N part.
Precisely. Now, Bellman-Ford, it works differently. It's good if you know you only need paths with a small number of edges, say at most k edges. It runs in OK time.
And critically,
Critically, it doesn't need a priority queue, doesn't sort, it just iteratively relaxes edges across the whole graph, k times.
okay, so Dijkstra's is smart about picking the next node, but gets bogged down sorting a large frontier. Bellman-Ford avoids sorting, but is maybe less targeted.
Kind of, yeah. So the question is, can you use Bellman-Ford's non-sorting nature to somehow shrink Dijkstra's frontier problem?
And that's where frontier reduction comes in. How do they actually do that?
This is the core idea, and it's pretty clever. They introduce a parameter, let's call it k. It grows super slowly, like a really small power of log n.
Think log N.
Okay, so k is small compared to n.
Very small. Then they look at a specific set of vertices. These are vertices whose true shortest path distance is less than some current bound B, and whose shortest path goes through some vertex that's already complete on the current frontier, S. Right, S is the set of nodes they're actively considering.
Exactly. Now, two cases. Case one, if this set S is already much bigger than at times the size of the frontier S.
So EC AS.
Yeah.
Yeah.
If that happens, they say the frontier is sparse enough, things are spread out, maybe Dijkstra-like processing is okay.
But what if it's not? What if S is small relative to the frontier size, like EC is KS? The frontier is dense.
This is the key. If the frontier is dense, they perform K-steps of Bellman-Ford style relaxation, starting only from the vertices in the frontier S.
Just K steps using that small parameter K.
Right. And doing this efficiently identifies a whole bunch of vertices, let's call them W, whose shortest paths are now fully determined using these short K-edge path explorations. They're done. Complete.
Okay, so they peel off a layer of easily reachable vertices.
Exactly. But here's the magic. The vertices left over, the ones whose paths weren't resiled by these K-steps, these are the pivots, P. They're like the starting points of potentially much longer, more complex shortest path trees that still need exploring.
And the clever part is,
The number of these pivots, P, is guaranteed to be much smaller than the number of vertices they just finalized, W. Specifically, P is at most WK.
because K is small but greater than 1, they've significantly shrunk the number of hard points they need to track. They reduce the effective frontier size.
Precisely. They've traded K steps of cheap Bellman-Ford relaxation for a much smaller set of vertices to handle recursively.
And this isn't just done once.
No, this whole frontier reduction idea is embedded within a larger divide-and-conquer framework. They have multiple levels of recursion, maybe log n t levels, where t is that log n factor again.
So they keep applying this reduction, refining the distance estimates layer by layer.
Exactly. It progressively finds the shortest paths without ever needing to do that full, costly, sort of the entire frontier like Dijkstra sometimes has to.
Okay, that's a really neat conceptual trick. Let's touch briefly on some of the technical gears that make this machine run smoothly. They use terms like complete and incomplete vertices.
Right. Simple idea. du is the true shortest path distance to vertex u. But u hat is the algorithm's current estimate. If du fel u equals du, the vertex is complete. Its shortest path is finalized. Otherwise, it's incomplete.
Makes sense. And they also make an assumption, or rather a transformation, about the graph structure itself, something about constant degrees.
Yeah, for the analysis and the core algorithm description, they assume the graph has been pre-processed so that every vertex has a constant number of incoming edges in degree and outgoing edges out degree.
But real-world graphs aren't usually like that. Some nodes are super connected, others barely.
Totally. But that's okay. There's a standard classical technique to transform any graph into one with this constant degree property without changing the shortest path distances.
How does that work, roughly?
You essentially replace high degree vertices with small cycles or structures of new vertices connected by zero-weight edges. It preserves the path lengths while making the degree bounded. It's a standard pre-processing step, so the algorithm's core logic can rely on that constant degree assumption, which simplifies things.
Clever. Okay. And another technical point. Unique path lengths. They assume paths have unique lengths to avoid ties.
Yeah, mainly for simplifying the proofs and ensuring the shortest paths form nice trees. If two paths had the exact same length, which one do you pick? It gets messy.
So how do they handle that?
They use a standard tie-breaking trick. If lengths are equal, compare the number of edges. If still equal, compare maybe the vertex ID of the last node, then the second to last, and so on. It's like sorting lexicographically.
Like sorting words in a dictionary.
Exactly. It imposes a total order on all paths, guaranteeing uniqueness without actually changing the shortest path length itself. It just makes the shortest path unique.
Got it. Okay, so inside the algorithm, there are key components. One is called Bounded Multi-Source Shortest Path, or BMSSP.
Right. Algorithm 3 in the paper, think of it as the main recursive engine. It doesn't try to solve everything at once. It takes a level L, like the recursion depth, a distance upper bound B, and that set S of complete frontier vertices we talked about.
And its job?
Its job is to find the true distances, dV, for all vertices EV that are closer than B dV, and whose shortest path comes via one of the vertices in S. It focuses the search.
And the base case, the simplest version.
The base case, level LAO0, is basically a tiny stripped-down Dijkstra, they called it algorithm 2, run from just one source, finding only the closest k+1 vertices. Very localized.
Okay. And then there's find pivots, algorithm 1. That sounds like where the frontier reduction happens.
That's exactly it. This is the part that runs those K-Bellman Ford-like relaxation steps from the frontier S using the bound B.
And it's uploaded.
It outputs two sets. W, the vertices that got finalized, whose short paths were found by this process. And P, the crucial pivots, the roots of the remaining larger trees that still need recursive processing.
And that's where you get the PWK guarantee, the size reduction.
Exactly. That's the key outcome of find pivots. It finds some answers, W, and leaves a much smaller problem to solve recursively.
Now, to manage all this recursion, the sets S, W, P, the distance updates, that sounds like it needs a smart data structure. They didn't just use a standard priority queue.
No, and that's critical. A standard heap wouldn't be efficient enough for how they need to access and update data across recursive calls. They designed a specialized data structure.
What's special about it?
It's tailored for their specific operations. Inserting individual vertices, adding batches of vertices, batch prepend, whose paths are known, and efficiently pulling out the next set of vertices to process.
Pull. How does it work, roughly?
It uses a kind of block-based linked list approach, keeping blocks sorted, maybe with some balanced tree structure on top to manage bounds efficiently. It allows them to handle these operations with really good amortized costs.
Amortized meaning averaged over many operations.
Right. So a single operation might occasionally be slower, but over the course of the algorithm, the average cost is very low. It's engineered specifically to support the recursive structure and the find pivots routine, avoiding the standard heap bottlenecks.
It sounds like the data structure is really a cornerstone of achieving that final complexity.
Absolutely. The algorithm's logic is brilliant, but making it actually run that fast required this carefully crafted data structure.
So putting it all together, the BMSSP routine calls find pivots, which uses the K relaxations to shrink the problem. The results are managed by this specialized data structure, and the recursion continues, refining the bounds until all paths are found.
That's the gist of it, yeah.
And the final runtime, that OM-log23N, where does it come from in the analysis?
It's a balance. The total work done by find pivots across all levels of recursion is carefully bounded. It ends up being related to log NT, which is sufficient because K and T are small.
Okay.
And then the costs of the data structure operations, the insertions, and bash prepends are also analyzed. The total cost for those comes out related to m times powers of log n, like M-log23n and M-log13.
And the M-log23N term wins out.
Yeah, that term tends to dominate the overall complexity. It's a really tight, intricate analysis that shows how all these components interact to achieve that final bound.
Wow. Okay, stepping back from the technical weeds. This feels like more than just shaving off a bit of runtime.
Oh, absolutely. This isn't just an incremental tweak. It's a fundamental shift in understanding for a problem people have studied for, 60 plus years?
It really challenges that deep-seated intuition that finding all shortest paths must involve sorting them somehow.
Exactly. It shows that if you only need the distances, maybe you don't need the order. And that opens up possibilities. Are there other problems with similar sorting barriers that maybe aren't real barriers after all?
It definitely sparks new research questions. It's a reminder that even in these foundational areas, there can still be major breakthroughs.
Definitely humbling, yeah.
So let's bring it home for our listeners, especially those in AI and ML. Why is this evolution of a fundamental algorithm like SSSP relevant to you?
Well, think about scale. A lot of AI and ML involves massive graphs, social networks, knowledge graphs, interaction networks in biology, the state spaces in reinforcement learning. They can be huge.
Right, billions of nodes or edges sometimes.
Exactly. And computations on these graphs, especially path finding or distance-related calculations, are often the bottleneck. If you're building, say, a graph neural network that uses path information, or doing large-scale network analysis.
A faster core SSSP algorithm could actually mean your models train faster, your analyses run quicker?
Potentially, yes. It might enable larger models, more complex simulations, or faster real-time decision-making in systems that rely on pathfinding, like logistics or robotics planning.
It's not like you just swap out Dijkstras tomorrow and everything gets faster, necessarily.
Probably not directly, no. The constant factors might be large initially, or the algorithm might be complex to implement perfectly, but the theoretical advance is huge. It pushes the boundary of what we know is possible.
And it reinforces that idea of revisiting basics, right? Combining old tools like Dijkstra and Bellman forward, but in a totally new way.
Yeah, it's a fantastic example of algorithmic creativity, taking established components and reassembling them with a fresh perspective to solve an old problem differently. That's innovation.
So here's a final thought to leave you with. If a problem as core, as seemingly done as single-source shortest paths can have its decades-old assumptions challenged and barriers broken, what else are we taking for granted? Are there other fundamental algorithms, maybe in data processing, optimization, even within specific ML techniques that have their own hidden sorting barriers or similar perceived limits?
Limits that maybe aren't as solid as we think.
Exactly. Could we apply this kind of hybrid thinking, combining different algorithmic paradigms to unlock new levels of performance elsewhere?
It's definitely something to ponder. We really encourage you to check out the full paper. The technical details are fascinating, a real masterclass.
And maybe think about your own work. Are there any bottlenecks you face where maybe, just maybe, combining techniques in an unexpected way could lead to a breakthrough?
The landscape of what's possible just got a little bit wider. It's an exciting time for algorithm design.